So far, in all of our example problems, we've only seen cases where forces align along the same axis. So in the last elevator problem, we had maybe a contact force pointed up and a different value, weight vector pointed down. But when it comes to finding the net amount of force, we didn't actually have to treat the forces as vectors. It was pretty simple just to note that we can take the difference between the two. I think we saw some earlier example problems where there was the thrust of a rocket and the air resistance pointing back in the opposite direction. When you have two forces pointing along the same axis, it's easy to find net force without doing any vector math whatsoever. So let's try an example problem where we have to take into account the vector nature of force. So here we have a lawnmower being pushed across the lawn with a force of 75 newtons, directed at a 45-degree angle. Let me turn this into some sort of picture. Okay, so we make a crude example here of a lawnmower. Okay, so sketch this situation and draw two free body diagrams. One without resolving the vectors and another one with the vectors resolved. Well, this language of resolving vectors just means anytime you have a vector that points at an angle relative to the x and y axis, that you want to break that vector into its components. So this is the kind of thing we did in our study of projectile motion. If we said you kick a soccer ball with some initial speed v naught at an angle theta, we resolved the vector by finding what was the component of that velocity along the x-axis and what was the component of that velocity along the y-axis. So in the same regard, we can find components of force vectors, and in doing so, we say we've resolved the force vector. So let's do it. Let's draw two free body diagrams. So that dot represents the lawnmower. So what are all the forces that are acting? So this will be the first case. One free body diagram without resolving. So you've got to brainstorm a little bit. Maybe it helps to name them. Let's see. There's contact between the lawnmower and the ground. And keep in mind, that's electrostatic in nature, right? All contact forces are really due to the fundamental force known as electromagnetism. Of course, there's another fundamental force at play here. There's not just a contact force, there's a force of gravity. So we're going to represent that as a downward vector. And then there's also the push down and to the left from the handle. That's also electrostatic in nature. So there's the push from the handle, there's the push from the ground, and there's the pull of gravity. So we just need to draw all three of those on our original free body diagram. So there we go. We're going to label this one as mg. Then we've got another force. Now, notice this appears to be one option to show the push, but the way we always make free body diagrams, we never put the tip of the force vector on the dot. We always put the tail of the force vector. So let's fix that. Let's make this a proper free body diagram and show the push like this, so that the tail of the vector coincides at the origin of our free body diagram. So we'll just call this, we'll just call it F. And then there's the contact force from the ground. That's going to point upward. Now you might think, okay, I've seen this sort of thing before. The ground pushes up on the lawnmower just as hard as gravity pulls down, so I'm going to draw these of the same length. Well, there's a problem with that, and you might see it. This force has a component along the negative y-axis. And so the normal force from the ground actually has to be longer than we drew it in order for the acceleration to only point along the x-axis. And I'm sure that's the case when you push a lawnmower, right? You might have an acceleration parallel to the ground, but there's not going to be any component of acceleration along the y-axis, right? So you have to take the time to conceptualize like this when you make your free body diagrams. So the length of the arrows in your free body diagram are not arbitrary. Drawing free body diagrams forces you to confront the concepts involved in the problem. Oops. So there it is. I think the normal force is going to be greater in magnitude than mg. So we've done part of the work here. We made a free body diagram that doesn't resolve the vectors into components. But anytime you have some force at an angle, it's probably a good idea to make a second free body diagram in which the forces are resolved. So nothing needs to be done to the vector that represents normal force. It already lies parallel to the y-axis. Likewise, we don't need to resolve the force of gravity. It's on the negative y-axis. But the applied force along the handle has a component parallel to the negative x-axis, while simultaneously has a component along the negative y-axis. So we can call this F subscript y and F subscript x. But you see, when I show those vectors on my original free body diagram, it might fool you into thinking that there are 1, 2, 3, 4, 5 overall forces. And that's just not the case at all, right? There are really only 1, 2, 3 forces, but we have one of those 3 broken into components. So it's better to actually draw a second free body diagram. So there's a force vector this way. That's one of the components of the push along the handle. There's Fx. Then there's also another force this way, and that's Fy. And so it's pretty clear as far as the mathematics are concerned that we're just simply going to add Fy and mg together since they point in the same direction. And the combination of those two is probably going to be equivalent to the upward value of n, because after all, I don't expect any acceleration along the y-axis. So let's see. I guess what I'm trying to say is if we take this vector that represents Fy, and what if we, instead of drawing it like this, what if we erase that and try to draw that same one, but instead of putting its tail at the origin of the free body diagram, what if we drew that Fy so that we connected it with the mg? Then hopefully you can see that that length in the negative direction and this length in the positive direction are equal. And so the net force, at least along the y-axis, is 0, but we're left with some unbalanced net force along the x-axis. Okay, we got part A done. Part B, what's the normal force? So, right, if this is true, so this is sort of implied, right? We had to assume that that's the case. But that's a pretty good assumption. The only way that can be true is if the normal force is equal to the sum of mg and Fy. So our normal force is mg plus Fy. Now, how can we calculate the value of Fy? Well, let's look back at this kind of messy diagram here. We have the overall force at an angle, which was given in the problem. We're told that that amount of force is 75 newtons and it's directed at 45 degrees. So if we draw that force on the xy axis and we try to show those components once again, that's Fx, there's Fy. We could also draw that same Fy over here. It doesn't change its length or its direction. So we really have a right triangle with a hypotenuse of 75 newtons and an angle of 45 degrees. Or we could express the angle all the way off the positive x-axis, and then in that case we'd say the angle is 225 degrees. So Fy should just be equal to the total force multiplied by the sine of the angle relative to the x-axis. So we get 75 newtons multiplied by the sine of 225 degrees. And this gives us negative 53 newtons. Now what's the negative mean? Well, the negative just reminds us that it's pointing in the downward direction, okay? But when I plug that in here, I'm not going to plug in negative 53. I've already dealt with the fact that it points downward by knowing that I need to add it with mg, not subtract it. So, yeah, a point of caution with making free body diagrams is make sure you're conceptualizing the directions implied by all the vectors and treat the math accordingly. So the normal force should be equal to mg plus 53 newtons. Now, mg, we're told that the mass of the lawnmower is 30 kilograms. So this is 30 kilograms. Let's go ahead and call g 9.8 plus 53 newtons. Okay. So we get a total normal force of 347 newtons. Remember, this word normal force means contact force. This is telling us how hard the ground is pushing up against the lawnmower. Last part, C, how much frictional force would provide a constant acceleration of 0.6 meters per second squared. Oh, maybe we made a mistake in our free body diagram. I assumed that there were only three forces: normal force, weight, and the push along the handle. But it turns out there must be more. This problem tells us that there's a frictional force involved as well. So let's change our free body diagram. We've got the normal force. We've got mg. We have a downward component due to the push along the handle. Let's do this. Let's use closed arrows for original forces and open arrows for force components. Okay, we'll call that Fy. We have Fx, and then we have back in this direction, I'm going to draw it smaller. How about lowercase f to stand for friction? Why did I draw that smaller? Because we're told that we have an acceleration, right? So the lawnmower is not being pushed with a constant velocity. If that were the case, I would have drawn the friction force exactly equivalent in length to F subscript x. So we already determined that the normal force cancels out the combination of mg and Fy and is equal to 347 newtons. Because this angle is 45 degrees, that's the case where the vertical and horizontal components are equal to one another. So we can skip ahead and know that this Fx is equal to 53 newtons. Now you might say, why didn't you call it negative? Well, in a way I did call it negative by showing that it points to the left and not to the right. So if we just stick to forces along the x-axis, this problem will be fairly easy to solve, and we can do that because we know that the normal force canceled mg and Fy. So we're really left with two remaining unbalanced forces, and it looks like the net force in this case, and there's nothing wrong with us saying that to the left is positive. If that's the case, our net force would be Fx minus friction. By Newton's second law, we replace net force with ma. So ma equals Fx minus friction. If we read the problem again carefully so we know what we're being asked for, what is the amount of frictional force that provides a given acceleration? So if we have to solve for F, we find the friction force is equal to Fx minus ma. So there we have it. We just need to plug in the numerical values. Our friction force is 53 newtons minus 30 kilograms for mass. Right, 30 kilograms minus 30 kilograms times 0.6 meters per second squared. That was just given. 30 times 0.6 gives us 18. A kilogram times a meter per second squared is a newton. So 53 minus 18 gives us a friction force of 35 newtons. Let's do one more problem along the same lines. So gain some more practice in treating force as a vector. So this time we've got a wagon. It's pulled across the concrete. We're going to assume that the ground is level, and we have a rope that makes a 30-degree angle. Okay, so there's our rope. We've got a wagon with a mass of 100 kilograms. The tension in this rope has a magnitude of 300 newtons. The rope makes an angle of 30 degrees, and there's a frictional force of 200 newtons pulls back this way. Okay, so I think we've got all the numerical values in the problem. We've turned the word problem into a picture. Let's see if we can take it step by step. Part A, sketch the situation. We've got that. Draw a free body diagram. Okay, so how many forces? Well, there's the tension. That's pretty clear. There's the weight of the wagon. Weight is a force. There's a friction force. And there's also some normal force. Now, what do you think? It's only the tension I'm going to have to break into components if I draw a resolved free body diagram, right? That means there's going to be a forward component to this tension, and there's going to be an upward component. Now, it looks like that upward component is not quite as great in magnitude as the downward pull of gravity. So, does that mean our wagon is going to be accelerating downward? No, we've left out another force in this diagram, right? We forgot to put in the contact with the ground, the normal force. So how long should we draw the normal force vector? I would argue we draw it just long enough. If this represents Tx, the horizontal component of tension, and this represents Ty, then we just need to add a little more along with the Ty so that the total combination of upward vectors offsets the downward pull of gravity. So that difference is made up by the normal force. So I've made things messy. Let me just go back. I don't need to break the tension into components just yet. I just wanted to think that through out loud so you can understand how I know from the get-go to probably draw the normal force as a vector that's only about that long. Okay, so with more and more practice in free body diagrams, you'll start to get a feel for how long you should draw the force vectors, as long as you really take the time to conceptualize and think through the problem in that way. But yeah, we want to make it a resolved diagram. So no change to the friction force, no need to break gravity into components, no need to break the normal force into components, but I want to show only the component of the tension along the x-axis as well as the component of tension along the y-axis. And you have two options. I could have drawn it so that that tension along the y-axis and the normal force are connected tip to tail with each other, and so I can show that the overall upward vector offsets the pull of gravity, so it would look something like this. And by the way, it's not necessary, there's nothing implied about the problem that the horizontal tension and the friction force are equal, or is there? Are we told that the wagon is pulled with a constant speed? No. If we were, then I would know to draw tension along the x-axis and friction equal in length. But it very well could be that the wagon is accelerating to the right. Okay, downward is our pull of gravity, and then I could draw upward two vectors that add together so that their overall upward value matches the downward pull of gravity. These two values, of course, would be the tension along the y-axis and the normal force added together. So either option 1 or option 2 are valid expressions of a resolved free body diagram. Okay, so we sketched the diagram, and we've made not only the original free body diagram, but also a resolved free body diagram to go with it. Part B, what's the weight of the wagon? Well, that's just a matter of calculating the value of mg. So if it's 100 kilograms and acceleration due to gravity is 9.8 meters per second squared, this is obviously just 980 newtons. Part C, what are the components of the tension? So if we take the tension vector by itself, draw it on the xy axis. If the angle is 30 degrees and the tension is 300 newtons, then we're just trying to figure out what's Tx and what's the value of Ty. Well, Tx is going to be T times cosine theta, and Ty is T sine theta. So if we multiply 300 newtons times the cosine of 30 degrees, we get a value of about 260 newtons. And of course, the sine of 30 degrees is 1/2, so this is going to be mental math, 150 newtons. So we got our components to the tension. Part D, is the normal force equal to, less than, or greater than the weight of the wagon? Well, you can see this vector represents the weight of the wagon. This vector represents the normal force, and it's pretty clear then that the normal force is less in magnitude than mg. Maybe we can put absolute value so we know we're talking about just a comparison of magnitudes. Okay, and lastly, part E, what's the magnitude and direction of the net force on the wagon? So when we look at this resolved free body diagram, we already showed that the combination of normal force and upward tension is canceled by mg. So that means all of those forces are wiped out, and then all you're left with is a tension to the right of, what did we say, 260 newtons, and a friction force back to the left, which is already given, I believe, as 200 newtons. So it looks like we have a net force. It's just found by subtracting the horizontal tension minus the friction. We take 260 newtons and subtract 200 newtons in the opposite direction to get a net force of 60 newtons. Now there probably should be a part F to this problem that says, what's the acceleration of the wagon? At this point, it would be easy. Acceleration is net force divided by mass. So our acceleration would be 60 newtons divided by 100 kilograms, which would give us 0.6 meters per second squared. So you can see the value of making a free body diagram. In the end, Newton's second law requires we divide some amount of net force by mass to get an acceleration. But determining the net force is not so straightforward, right? Sometimes we have to find net force by making vector diagrams. So thanks for tuning in.